office. But I didn't take you up on your offer. But, I mean, it's not a bad idea, right? If I hand-selected a group of students, had them take the exam, sign a non-disclosure agreement. Yes, I should get former students to take my exams, right? Like pay them a couple bucks. It'd be great. Oh. All right. We have an exam review tonight at 6:30, I think I said. I can't record it because I'm incapable of doing so, apparently. So show up, ask questions. It's an hour and a half of my evening time dedicated to you, the students, that you do well, because I care. We were talking on Monday about Raman spectroscopy, and I'm not gonna sugarcoat this. It's weird, right? As an effect. Essentially, what's happening is all right. Anyway, essentially what's happening is I turned my sound back on because that way you don't have to email me, you can't get in. Light scatter occurs because the electric field of an electron cloud repels the electric field of the photon, which is an electromagnetic wave, correct? So when those two interact, most of the time, it's elastic in that the energy of the photon does not change. And in a very small subset, about one out of every billion photons, 10 to the 9 photons, you get an inelastic scatter. And so what happens, if you are plotting this on a wavelength scale, yes? Was that, I don't know what that was, but was that intended for me or no? I'm guessing no. Okay. If we look at wavelength, right, in nanometers, we're going to have this, we're going to have a laser wavelength. This is the laser itself. And so if I measure light scatter, the majority of light is going to be at that laser wavelength. Okay, this is the elastic scatter. Okay. I'm going to change colors here. So this is my elastic scatter. So no energy is gained, no energy is lost. And so if you remember the equation for energy, and you better at this point, because I've talked about it so many times, and you may need it on Friday anyway, if the energy is the same, the wavelength of that photon doesn't change, correct? But what Raman discovered when he did his first experiments was he was actually looking at scatter of just pretty simple organic solutions. He would always see at a very intense Rayleigh peak, and then he would see other peaks that we now call Raman bands. And interestingly, he would see the following. He would see Raman bands on either side of the laser wavelength. So if you think about it, if you're seeing scattering at wavelengths, again, we're talking wavelength right now, this is important. If you see scattering at longer wavelengths, what does that mean about the energy of those photons? They vary, but if we're comparing them to the elastic scatter or the Rayleigh peak, what would you say about the energy of those photons relative to the original photon? They're lower, right? Exactly. So these are lower energy. So that photon has lost energy, right? What about the peaks that are on the higher side? They have higher energy, right? The scattering peaks on the longer wavelength or lower energy side are mirrored on the higher energy side. Exactly. They're less intense on the higher energy side, and we'll talk about why, but they're mirrored. And you'll notice in wavelength scale, the higher energy ones are closer together, right? Because the longer wavelengths are more spread out, cover the same amount of energy, right? It's like if I gave you a $1,000 bill, that's one piece of paper, right? If I gave you, that's a lot of money, obviously. If I gave you $1,000 in singles, that's 1,000 bills, right? Because each bill has less currency. I need more of them to cover the same amount of money. Does that make sense? So in the wavelength scale, I need to cover more nanometers on the farther side to cover the same amount of energy, okay? That's going to come back to be important later in this lecture, okay? So wavelength was kind of funky, but if you look at, instead of wavelength, look at energy. And since we're talking about vibrational spectroscopy, we're really looking at the frequency divided by the speed of light. And if you're really good at algebra, if you put your wavelength in centimeters and take the reciprocal of it, that gives you wave number, right? The units of this are reciprocal centimeters. So if I take this same spectrum and I plot it instead in what I'll call Raman shifts, this is my Raman shift in wave numbers. It's the difference in energy between the laser and the scattered light. And again, if you want to do this in math, you can do 1 over the laser wavelength minus 1 over scatter wavelength. I'm not going to abbreviate it as scat, because that, you all know what that is. Okay. All right. So let's look at this equation real quick and think about just elastic scatter, just Rayleigh scatter. In other words, photons that hit that molecule, scatter off, and neither lose nor gain energy, right? So they have the exact same energy. If they have the same energy, what does that mean about their wavelength or their frequency? If the energy of the scattered light is the same as the incoming photons, what would you say about the wavelengths? They're the same, right? And their frequencies are the same. So if I've got, if I just say that the laser wavelength is x, right? If I have 1 over x minus 1 over x, what is that value? Thank you, 0, right? So at Raman shift of, all right, at a Raman shift of 0 wave numbers, I have my Rayleigh peak. And then at longer wavelengths or longer Raman shifts, positive Raman shifts, I have, my Raman band, so cell draw 3. I will have on the other side, actually, I was drawing something false, right? On the other side, a much smaller version of that spectrum, but mirrored. I want to point out, we call these on the negative side anti-Stokes Raman bands, and we call these Stokes Raman bands. The same idea as a Stokes shift in fluorescence. So this is observationally what, yes, Jordan? Yeah, I'm about to get into that, but yes, yeah. So, and if it's still unclear, then ask. I don't mean to blow off your question, but good segue into my next part, actually. Thank you. I want to point out, though, real quick, when we convert from wavelength to frequency, because wave numbers are a unit of frequency, right? That's energy. So since the energy is the same, the spacing on either side is the same. So it is a mirror image in frequency space, even though it's not a mirror image in wavelength space. Does that make sense? Okay. If I may use my paper money example, $1,001 bills is equal to $1,000 bill, correct, in monies. But obviously one requires more paper because the paper is worth less per unit. But once I convert those into like electronic money, it's the same. Becca? Please, but just do it louder. Can you say that louder? It's so hard to hear. Yeah. The first one is not, it's mirrored but compressed on the low wavelength side. So it's like a squished version, whereas the spacing is identical in the frequency space below them. Yes, absolutely. But they're less intense on the anti-Stokes side. So Raman is a really weak effect. So before I get into the effect stuff, it's a very weak effect, a low signal effect. And Stokes shifts are always more intense than anti-Stokes shifts. So if you've got two signals, one is always weaker than the other, and it's a weak technique, you wouldn't pick the weaker one, right? Correct? All right, good. So we almost always work on the Stokes shift side, and we almost always plot our Raman spectra just on the Stokes shift. So we start off with 0, and then we get wave numbers. And then we have like part of this, Rayleigh peak, let's say. In other words, we just look at half of that mirror, if you will. These Raman bands are vibrational bands, vibrational frequencies. So if you've got like a hydrogen, right? Hydrogen vibrates at 4,000 wave numbers. That's the Raman scatter will lose 4,000 wave numbers by energy, basically, right? So how does this happen? So Raman first, actually two different scientists the same year observed this effect. It's named after Raman, who ended up getting the Nobel Prize because he not only observed it, but they both came up with mechanisms of why this was happening, and his was the correct one, okay? He's the first Indian scientist to receive a Nobel Prize. It's a pretty big deal because it's a technique that's still used today, right? Still named after him. It's pretty neat. So what happens in the Raman process? Okay. Well, it's weird. So let's consider a ground state. Let's look at the mechanism of Raman spectroscopy. Some people say Raman. I've never heard it called Raman. It's like when people say like either and either. I say either because I decided in 7th grade to be pretentious. I really did, and it's stuck with me since then. Let's look at the ground electronic state. I'll just draw some vibrational levels. And let's ignore an excited state. There's no excited state on this diagram because it's somewhere off the page, right? It's somewhere higher up. When we talked about absorbance, I was very clear that your wavelength of your light source must match the absorbance wavelength of the molecule. In other words, the energy you're putting in must match the energy difference between the start and end states of an electron, right? And I told you that if you don't have enough energy, nothing happens. And if you have too much energy, nothing happens. It has to be exact, right? Well, I left a little bit off there, right? What happens when a photon comes by? Right, so here's my molecule, A for analyte. A photon comes by and scatters off. It's not absorbed and emitted, right? That's very important. If you could go in with like a tiny subatomic label maker and put like, Jacob's photon and stick it on there, that same photon comes off, right? And so it's not absorbed. What happens when scattering occurs is most of the time you'll have in a particular ground state, you're going to have atoms or electrons, that are in different vibrational states, right? So these are different vibrational states. Thinking about the Boltzmann distribution, remember that? I hope so. Really hope you remember the Boltzmann distribution. Okay, good. If at any given temperature, do you expect lower states to be more populated of those vibrational levels or higher states to be populated at most temperatures? Lower, right? Because it's an exponential requirement, right, on temperatures. You have to get really hot to populate upper states. That's why we use plasma sources for atoms, right? So in general, there are more molecules in the lower vibrational states of that window of possible levels. So here's what happens, right? There are 3 things that can happen. Case 1 is the Rayleigh case. What happens mechanistically, okay, I'm going to get a little metaphysical here. I'm going to describe something that doesn't happen, but we use this process to understand Raman because it's that hard to figure out. Okay. What happens is when a photon comes by, your molecule goes up to a non-existent virtual state. A virtual state is exactly what it sounds like. It is an electronic level that doesn't exist. I warned you all that it's going to get like kind of Doctor Strange level weird in this class, right? And so what happens with that particular molecule is, I'll tell you this: if you philosophically speaking, if you're moving a molecule from a state that exists to a non-existent state, what is the probability of that happening? 0, right? It doesn't happen. Yet it does, right? So what happens is, and I'll explain more in a second, we call this a virtual state. We pretend temporarily that we move a molecule to this non-existent state. If this state doesn't exist, how long can this molecule possibly stay there? It can't, right? So instantaneously, and scatter is instantaneous, instantaneously this molecule returns back to the exact same state it started from, having neither gained nor lost any energy. What actually occurs is those two electric fields interact and they inductively couple temporarily, just like your induction stove, or if you have an Apple Watch or a wireless phone charger, right? You inductively couple current between the two devices. The electric fields basically scramble each other temporarily, and they go their separate ways, but return to their original state. All right? So it's a perturbation process, and it's not that friendly. The Stokes case, or Stokes-Raman scatter, if you will. We never really say Stokes-Raman when we're talking about Raman. We're either talking about Raman spectroscopy or anti-Stokes Raman. Okay, but Stokes-Raman spectroscopy is when you go from a lower state, a lower state to that same non-existent virtual level, and instead of returning to the state you came from, you go to a higher state. What physically happens to the molecule is this electric field comes by, scrambles its electron cloud, and as that happens, the molecule rearranges itself and is now in a different vibrational state. That scrambling and that rearrangement takes some energy from the nearby electric field as they're coupling with each other. This is weird. I get it, right? I can tell half of you are like, what? And that's okay, right? That's what we're talking about it kind of in this detail. The reason that Stokes-Raman is more common is because you're going from a lower state to an upper state, and the lower states are more populous, correct? Because it's strictly a Boltzmann thing. Then there's a third case of anti-Stokes-Raman. I guess Stokes should be capitalized. It's named after Stokes, but it's fine. Where you go from a higher state, let's say here, to the virtual level, and then back down to a lower state. Now, if you look at the anti-Stokes case, the molecule has lost energy, right? And the photon, if you look at it from a vector perspective, has gained energy. So in the anti-Stokes case, the photon leaves with a little bit of extra energy, and that little bit exactly matches a vibrational level. So when I plot it as delta nu, I have vibrational bands, just like I would in IR. In the case of the Stokes-Raman case, my photon has lost energy because my molecule has gained energy. It's like the stock market, right? If you're making money, someone is losing money. There's only a finite amount of money out there, right? Why do we use a virtual level? I don't know. I wasn't alive. My parents weren't alive, right? But it's actually kind of a convenient way of thinking. It's also, if you think about it also, it's a non-existent level that you don't actually go to for a 0 period of time. So this process isn't something that you would deem to be likely to occur, and it is not. Raman spectroscopy is not favorable from a statistical standpoint. For every, like I said, every 1 billion with a B photons you fire at this thing, you get 1 Raman photon, right? So it's very weak. Because it's so weak, you have to get a lot of, you have to kind of use a really high performance instrument for it. So you get, so Raman gives us vibrational bands. What do we use vibrational bands for in the IR? Like, what do we use IR spectroscopy for? To identify structure, right? Thank you, Jacob. Yeah, identify structure. So you can do that with this. They're analogous, right? They're not exactly the same, though. They don't give the exact same spectra. So I have in your notes the spectrum of Indene, both the IR and Raman spectra on the same graph. And if you look at it very closely, you'll notice some of the peaks are the same and some are missing, right? So there are some selection rules. Don't you love that word? Just saying that brings me back to PChem. For the IR, a vibration needs a change in dipole. In Raman, vibration needs a change in polarizability. What's a dipole? I know you know this, so I'm asking you because I know you know. This is a kind of professor question where this is quizzing you. What's a dipole? It's like you said, electronic deficiency in one direction, right? It's basically a polarization within the molecule, right? An uneven distribution of positive and negative charge, right? Yeah, excellent. Mikhail, you got to lock that down. He's smart, right? Thank you, Grace. That made my day. I swear, I'm going to get so many teaching evaluator comments. Dr. Pappas seems obsessed with Michaela and Colton's relationship. It's just funny, and they're good sports about it, right? So I'm going to use it to my advantage. Yeah, it's absolutely a distribution of electrons uneven, right? So if you look at water, for example, water is horrible in the IR. It absorbs so much. This funky little molecule should be linear, right? Except for those extra lone things. And there's nothing more electropositive, or nothing more positive, if you will, than a proton. And so this molecule is a fairly negative atom with two protons sticking off one side of it. And so it tends to do weird things like fall in lockstep with itself. Water should be vapor at this temperature on our planet. There should be no liquid water above like minus 70 Celsius. If you actually plot, and make my freshmen do this, if you plot like atomic number of every other element in the row on the periodic table and their melting and boiling points, and you extrapolate what water should be by its atomic number, it should be gas, like even at minus 70 degrees. But it's that cohesion because of the electronegativity that makes it, it's that high polarity, right? So this molecule has a pretty significant dipole, correct? And any vibration you can think of, any bending of a bond, any lengthening or shortening, symmetrically or asymmetrically, radically changes the dipole of water. So it is extremely IR active. In other words, its stretches are actually very prominent. And it absorbs over such a large range of energies that you can't really work with aqueous samples very well in the infrared. Tissue samples, a lot of biochemical things, solutions of proteins and enzymes, things that are interesting, right? Let's look at a simpler molecule. Hydrogen, the simplest of all molecules, right? It's got one bond. How would you describe its dipole? Well, I mean, it's a covalent bond, but how would you describe the dipole of that molecule? Say it louder. Maverick, are you single? You are? Maverick's single, everybody, and he's smart too. So if you're looking for a smart dude with a cool name, if you get a date this weekend, you owe me, all right? Like lunch. All right. It's non-existent because it's a symmetrical molecule. So it is not IR active at all. You can't see the one stretch of hydrogen in the IR. It's invisible to the IR. Well, let's look at the Raman case. In Raman, we need a change in polarizability. Well, what is polarizability? Who said that? Jackson? It's the ability to become polar. I mean, you're actually correct, but not exactly what you're thinking, right? The polarizability is the deformation of the electron cloud. It's non-resonance. In other words, if I've got a molecule, let's say, yeah, here's my hydrogen molecule, right? I guess that's not a real goal. I don't know. What does a sigma bond look like? Is it a sphere? No, it's like a weird it's not a globe though, isn't it? Like a, I don't know. Does anybody know what a sigma bond looks like for real? I can't remember. Is it a dumbbell? No, it's. You know what? We're gonna not worry about it because I have not thought the phrase sigma bond has not entered my mind in this century. Colton, you want to come up and draw it? You want to come up and draw it? Yeah. Seeing you proud. I'm just gonna have a seat.
And do you want it for the hydrogen, for the H2?
Yeah, for hydrogen.
Okay. It would be like 2 hydrogen atoms and their overlapping circles.
That's a sigma bond?
Yeah.
Some of you are wondering, why am I paying tuition if Dr. Pappas doesn't have a sigma bond? Man, I'm so specialized now, I can't think about that stuff. I have colleagues who are always like, well, I bet you can't remember Dale's Alder reaction. I'm like, are we really going to bust out like what things we remember from undergrad? Because quantum mechanics is going to kick your ass, and I'm good at it, right? So, thank you for the sigma bond. This bond, if it stretches, right? If there's no symmetric or asymmetric, it's a single bond, right? If it stretches back and forth, what happens to the size of that electron cloud as a function of time? Would it not also change? Yes. The larger the electron cloud, the more deformable, the more polarizable it is, right? So you can think about a change in polarizability. The way I like to think about it, as a change in size of the molecule. So now looking at hydrogen, as it vibrates back and forth, there is no dipole change because as Maverick very astutely pointed out, there's no dipole, right? If it doesn't exist, it can't change. It's non-existent. In the case of its stretch, though, it does change in size. Water, the water symmetric stretch will actually cause a polarizability change and is visible in the Raman spectrum, but it's pretty weak. But all those other things like bending of that bond don't change the size of the molecule at all. And so most of the stretches that water can undergo are IR inactive. So I'm sorry, Raman inactive piece. So the real key point here is that Raman is not strongly active in water. Water is where everything interesting happens as far as we are concerned, right? Now, my organic colleagues would disagree. And I'm not downplaying what they're saying, but you can think about it from a perspective of your very existence is basically, you're basically a bag of water and some chemicals supported by, a mineral endoskeleton. I mean, I guess we all are, not just you, right? So that's important to think about, right? Because Raman is a weak effect, let's talk about its instrumentation briefly, and then we're going to be done with spectroscopy. By the way, Raman is not on this exam. I know you know that, which is why I think some of you aren't here today. All right. Because it's so weak, there's not much room for interpretation. You can build a UV visage in many different ways. You can use an LED light source or a lamp. So that is an excellent question that I should have addressed. Thank you. The question is, are stretches either Raman or IR active? And the answer is no. There are some that are only active in one mechanism, and there are others that actually match. So if you go back to that Indian spectrum in your notes, you'll notice there are a lot of peaks that overlap. Those are the peaks that are IR and Raman active. So you can have some that are both, some that are only in the IR, and some are only in the Raman spectrum. That's an excellent question. Thank you. All right. So getting into instrumentation, there's no room for interpretation. You can only make Raman in so many ways. The light source has to be a laser. I mean, it wasn't before lasers were invented and nobody used Raman because it's so weak and I only get a 10 to the minus 9 output of the photons I put in. I need to put in a lot of photons. And there's no better way to get a whole lot of light into a sample rapidly than using a laser. Okay. The Rayleigh peak is quite large. And that makes me sad because it's a source of noise. So we use what's called a notch filter to attenuate it. A notch filter in spectroscopy is the opposite of an interference filter. An interference filter, remember, only lets in a certain number of wavelengths, correct? The notch filter has high transmission except at the laser wavelength. And so if you're using a laser at 635 nanometers, for example, you would have a notch filter at 635 nanometers to absorb light. So the way it would work, if you have a laser, you have a sample, you tend to collect light in a backscatter geometry because you get more scatter that way. And then that light goes through a notch filter. And its job is to just attenuate that, that Rayleigh peak. Before this, it was actually very hard to measure Raman scatter that was low wave number, lower than a few hundred wave numbers, because it's too close to the Rayleigh peak, and the Rayleigh peak is gigantic, right? It'd be like, I mean, it would be like walking through the airport, minding your own business, and then right next to you is the president of the United States of America. No one's going to be like, oh my God, Jackson's here, right? I mean, everyone's going to know it's the president because more people know he is, right? Jackson's like, I don't know, maybe, right? Right. And then the rest of this light goes to the monochromator. Okay. The monochromators that we use are all short focal length. We sacrifice a lot of resolution because if you remember talking about focal lengths, shorter focal lengths are higher signal throughput, right? And then the detectors are always CCD detectors. Before CCDs were available where you could acquire all that, it takes a long time to acquire a Raman spectrum anyway. And when we used to scan, I remember I did a Raman spectrum when I was an undergrad that took 48 hours. I mean, I didn't watch it the entire time, but I hit go, and then 2 days later it was done. And if you found out that something was wrong with your sample, or then you just wasted 2 days of your life. With an array detector, that same measurement takes 2 minutes, so much faster, right? So it was the combination of lasers, and in the 1990s, using CCD detectors for as an array allowed us to acquire more signal and get better signal to noise. There's a technique called surface enhanced Raman that I'm actually not going to talk about this year because it has been, we've been talking about it as this thing that's about to happen, about to make a big deal. I say we as a scientist. Since I was 7 years old, I was riding my big wheel through my neighborhood at that time. I wasn't really doing any science yet, but it still hasn't delivered in 37 years. So I'm going to skip it for now because I am kind of running behind this semester. I blame Zoom. Not people on Zoom. I just think this is a weird format for teaching. All right, so I want to talk about N spectroscopy, right? And talk about mass spectrometry instead. But before I get into mass spectrometry, I just want to highlight Raman allows you to do so much qualitative measurement because it's a vibration technique that you couldn't do in the IR. They do things like forgery of ink. Someone forged your signature and you don't use that kind of, like all of your other documents are signed in the same kind of pen and ink, they can tell. If you fired a gun recently, they can actually take the gunshot residue off your hand and use Raman spectroscopy to identify the manufacturer of the actual ammunition, right, based on the molecular traces that are left behind. You can determine cremains. You all know what cremains are? Any forensics people in the room? No. Burnt up corpse material called cremains. Cremated remains. So you can do all kinds of things. You can actually take a tooth out of a corpse and tell how old it is using Raman. So it's a pretty neat technique. Okay? It's used in the pharmaceutical industry all the time. But I want to shift gears and talk about mass spectrometry entirely. We talked about electrons at first, right, in electrochemistry. Move electrons around. Then we talked about, but I mentioned that the electron doesn't have any actual information, right? Like an electron coming from a titanium atom is just an electron. It doesn't maintain a signature that says I came from titanium. Spectroscopy, we look at photon energy, which tells us a bit about the molecule, right? But the problem with that is I can't really control photons, right? I mean, I can collect them, but I can't make them bend to my will, right? So if only we had a way of, having the controllability of an electron with the information of photon, and that would be mass spectrometry. If any of you took Dr. Meshrev's class, he's a big mass spectrometry person. He loves it. He'll tell you about how great it is. And it's actually a pretty cool technique, right? But mass spectrometry, we analyze molecules in the gas phase, I guess atoms too, right? Based on their mass to charge ratio. And that sentence is a Nobel Prize worthy problem right there. Because mass spec does analyze molecules based on mass to charge in the gas phase. So if we're looking at a mass to charge ratio, obviously molecules have mass. Do all molecules have charge? They don't, right? I can think of one that doesn't, water. Can you all think of one that's not water? Of course you can, right? Benzene. We can do this all day. We can all just name molecules that aren't charged. So most molecules aren't charged, and they're also not in the gas phase. So getting your molecule, we're looking at ions, right? Mass spectrometry measures ions. And I can control ions quite well because of Coulombic forces, right? When we talk about Coulombic forces, what are we talking about? What? Electrostatic attraction, magnetic attraction, and repulsion, right? We're taking advantage of the charge of the molecule. Now, when we talked about, what are some other forces we learned about in chemistry growing up when you were little chemists 3 or 4 years ago? London dispersion forces, right? That's a good one. Any other ones? Van der Waals forces. Dipole, yep. Dipole-induced dipole, remember that one? Is there another one that's pretty important? Was that? Hydrogen bonds, thank you. Make your hair curly, your proteins fold, not your protons, the proteins fold. These are all 1 over r to the 6th forces, where r is intermolecular distance. Is there another technique we just talked about that in theory could be on your exam on Friday that has a 1 over r to the 6th dependence? What is it, Jordan? That's great. I'm not being facetious. I take that as a correct answer that you remember, but you can't recall at this moment. But I know by Friday you'll be ready. Whenever they became together, what I would call Forster resonance energy transfer, or FRET. Yes, but I knew what you meant. Honestly, if you wrote in the exam when they came together, I'd be like, I know what you meant, right? Especially if you made like the finger motion of 2 molecules coming together, right? That was very indicative of it. I'm embarrassing you, I'm sorry. FRET is an r over the 6th dependence because you require molecular proximity, correct? London forces, Van der Waals forces, hydrogen bonds all require molecular proximity. 2 water molecules that are pretty far apart don't go, oh my God, I have to go over there and touch that hydrogen, right? Like, it doesn't work that way. In fact, if you think about it, if you've got 2 water molecules that are 2 angstroms apart and they move 4 angstroms apart, you just lost 1/64th of your hydrogen bond, right? That's a huge drop off. Coulombic forces, anything involving charge, has a 1 over r dependence. That is a much different effect, don't you think? If you double the distance between 2 ions, you just cut the force in half, not by 1/64th. So you can argue that it's 32 times stronger in that case, right? What does that mean? It means I can manipulate charged objects, in this case molecules, over large distances. Now, I'm not talking about miles. I'm talking about centimeters. But to a molecule, a centimeter is an infinite distance, don't you think? How big's a molecule on average? I mean, I know there's a range, right? But you've learned about molecular size in your other classes. What's the molecule size that sticks out in your head? Like a couple angstroms, right? So say you've got a 1 angstrom molecule over a 1 centimeter distance. That's 100 million times larger than the molecule itself, right? 10 to the minus 10, 10 to the minus 2, right? 10 to the 8th is 100 million. That's a huge distance. So we can manipulate this. We can't move any other object 100 million times distance without touching it, right? Bless you. So it's a huge deal, right, to move things around. So a typical mass spectrometer has the following building blocks. You need an inlet, your interface to the rest of the world. Then you need an ion source. The ion source takes your input and puts out ions. That's most of the magic. The Nobel Prizes that have been awarded for mass spectrometry, there have been several, have all been related to ion sources. Right? It's that big of a deal. Because putting something in the gas phase and giving it a charge is not easy. I mean, atoms are pretty easy because you can abuse an atom pretty much. But you couldn't take a protein and heat it up to high temperature. Like that wouldn't work, right? You have to do it some other way. After that, it has to go into the mass analyzer. The mass analyzer is sort of where you get the separation, right? So you separate ions at this stage, and then you have to have a detector. This is like the flow chart, if you will. Now, this part, the part that I'm going to highlight in pink here, is all done in a vacuum. That's why your mass spectrometer has an interface, an inlet, right? The instrument is done under a vacuum. Why a vacuum? Certainly not because we like complexity and mechanical failure, for sure. I misspelled vacuum the first time, didn't I? That was just one. I just want to add a lot of letters to vacuum. All right. Let's just consider for a minute an ion. And let's put a metal plate here with a positive charge. Let's put a metal plate here with a negative charge. Where's my ion going to go? To the negative charge, right? But what if I have gas molecules? Accidentally in there. I mean, it could be a torr, like, 1 millimeter of mercury. Not very much from our standards. We would certainly die at that vacuum. But a very small number of gas molecules in the way. And that ion is traveling in a straight path, right? What's going to happen to that molecule? What's going to happen to my ion if I have some gas molecules or gas atoms present? What? It's going to collide, right? It's going to be a collision. What will happen? Well, Duncan postulates your trajectory can alter. Or you can fragment the molecule. You can actually break it apart. Sometimes we do this on purpose, by the way. So I can fragment my molecular ion, or I can alter its trajectory. These are bad things. If I'm trying to make it go from point A to point B, and now it's hit something and gone a different direction, it may take more time to get there. It may arrive at a different point that I'm not expecting it to. So we have to conduct this under low vacuum, something called a mean free path. It's the distance between collisions. In theory, if you want to avoid collisions entirely, your mean free path must be longer than the travel path of the ions. That makes sense. If your mean free path is a meter and your instrument is 10 centimeters long, it has a very low probability, right? 1% probability actually of making a collision in that case. So that's what you want. Okay. Now, we use, in spectroscopy, we had all these different units, right? Like wave numbers and wavelength. We use the Dalton, what I used to call the atomic mass unit. What did you all learn when you were freshmen? Was it atomic mass unit or Daltons? Yeah, AMU. Yeah. So the AMU is renamed after John Dalton. Yes. When we want to break a molecule apart on purpose, which we'll do later on, we'll fragment it. Yeah, it'll be a little bit. I don't want to get into it right now, but basically, the mass of a molecule can tell you a lot, but it really can't tell you the identity, right? Because it could be made up of a different constituent of atoms, right? It could be the same thing. So that's why we do it. We intentionally do it at that point, but we want to control that. So the Dalton is named after John Dalton. Y'all know who he was? The plum pudding model of the atom, right? He's credited for the discovery of the atom, even though he didn't discover it. It was actually discovered or postulated by Democritus, 2500 BC. But because Socrates was his arch rival and was more popular, his theories all got trashed. So Democritus also came up with the concept of aesthetics, that there are things that are universally beautiful or good. There you go. And Socrates hated him. So then we had to wait like almost 3,000 years for someone else to go, I think I'll call that an atom. We would have had jetpacks by now, right? Once again, been denied. You can clearly tell I want a jetpack. So we use a Dalton as our unit, right? And we know that one Dalton equals one atomic mass unit that we taught you in Gen Chem, right? And that equals roughly 1.66 times 10 to the minus 24 grams, which is about 1/12 of a carbon-12 atom. Right? We've defined carbon as having 12 Daltons. Right, exactly. How many of you looked at a periodic table in the last 2 weeks? You know, they always have those masses, the actual mass, right? You know what that came from? Mass spectrometry. Every mass on the periodic table is measured by mass spectrometry. So that number you've been taking for granted since high school chemistry came out of mass spec, just so you're aware, right? Now, the composition or the number of Daltons of a molecule can kind of tell you what you're looking for in some ways, right? But not exactly. Because there are also isotopes. So for example, if you have methane made out of carbon-12 and hydrogen, it's 16.031 Daltons. What if I substitute my carbon with a carbon-13? It should be about 1 Dalton heavier, right? And it is, about. But what if I do something different? What if I keep my carbon-12 and I substitute a deuterium for a hydrogen? You would expect the mass to be exactly the same. Because what's between carbon-13 methane and carbon-12 methane with a deuterium, what's different? I have an extra neutron, no matter what, right? And that neutron was in a carbon nucleus at one point and in the hydrogen nucleus in the other, right? But really is not any, I mean, the mass of a neutron is the same. They're all the same. Yet if you look at the masses, I wrote down my notes wrong, sorry. They're different. So we can actually use high resolution mass spectrometry, like they do in the MESREF group and the GAMAS group, to actually look at those subtle changes. But let me ask you this question. Shai, I'm not going to ask you how much you weigh. That's a rude question. But if Shai weighs X pounds, if I give her a 25, she stands on the bathroom scale right here in class, she's mortified or happy or whatever, but it's embarrassing, right? No matter what you want. And I give you a 25-pound weight, it's exactly 25 pounds. How does her mass change? How does her weight change? It increases by exactly 25 pounds, right? So adding a neutron to this molecule shouldn't make a difference where it goes. It should be exactly 1 neutron heavier, yet it is not. In fact, if you take helium, simple helium, 2 electrons, 2 protons, 2 neutrons, right? And you add up its mass, it does not equal the masses of 2 protons and 2 neutrons. You can throw out the electrons, they don't weigh anything, right? It's actually lighter. That would be like giving Shai a 25-pound weight, and her mass increases by 18 pounds. How is that possible, right? It's called a mass deficit, exactly. Do you know what it's due to? Anybody know? You're just killing it today. Yeah, it's energy, right? How does you ever thought about, there are things I think about like at 3 a.m. when I can't sleep. And you know, it's like Have you ever thought about why a nucleus can possibly exist as an idea? I mean, what's more positive than a proton? Nothing, right? And you've done experiments your whole life, like charges repel. But let's take a bunch of the most positive thing in the universe and squish it together so it's literally touching itself. That idea shouldn't happen, right? The plum pudding model sounds pretty sweet at that point, right? Till Rutherford proved it wrong. So how can a nucleus exist, and how much energy is required to keep that nucleus from flying apart? The answer is substantial. So much that a few kilograms of material, when it fused together, can level a city, right? We're talking about nuclear binding energy. And when it's released, it's gamma rays. It goes through everything and kills everything in its path. So we're talking about phenomenal energy. Have you ever thought about where that energy comes from? I hadn't until one day. I was like, this weird question, like, how does nucleus stay together? The nucleus stays together through nuclear bonding energy. That comes from the mass of the neutrons. So when you squish together an atom with your godlike hands, right? Two atoms smashed together in the, or whatever, in the heart of the sun, that fusion energy, some of that energy comes from the mass. So the mass converts and becomes lighter temporarily. And so the mass of the neutron becomes nuclear binding energy. When that atom splits, the neutron is converted back into its mass, but energy is lost or gained depending on what's happening, right? That energy is substantial. So whenever you're talking about adding up, it's the only thing on Earth that if you add it together, the parts are always more than the sum, right? It's kind of weird. So just think about that. It's kind of weird that suddenly